for what your future outcome y might be. This best guess may either come from a physics-based numerical weather prediction model, but it doesn't have to be weather prediction, that's why I put it in brackets, but some physics-based model. It could be a statistical model, a machine learning model, for example, just for the mean of y given lots of covariate information. Or it could just really be a best guess, some expert who tells you, no, I mean, I think y is going to be 5 tomorrow. Now, one assumption that's kind of the guiding principle throughout this talk is that we hope that if we have reasonable predictions, we hope that if the predictions increase, we should expect an increase of the outcome. So that's the underlying assumption that I will use throughout. Now, what is our goal? Instead of just having the single value prediction, we somehow would like to quantify the uncertainty of y through a predictive distribution. So instead of issuing just a best guess, a number for y, we'd like to have a full statistical distribution for y. Now, what is this EasyUQ approach that we're trying to put forth in our work? Is that we're trying to use a distributional regression model for y given x that honors this isotonicity or monotonicity assumption that I've given above, namely that if the prediction increases, we expect an increase of the outcome. And the tool that we're going to use, the distributional regression method to achieve this, is called isotonic distributional regression. So what is isotonic distributional regression? So I will reformulate my goal a little bit. So this is my goal prime, so that I can put it in the framework of isotonic distributional regression. So the assumption is here now, if the covariate increases, and for EasyUQ, the covariate that we're interested in is a single valued prediction, we expect an increase of the outcome. Now, since we're in a distributional regression model, of course, we have to make sense of what it even means that the outcome increases. So here, what do we mean by this increase of the outcome? I hope you can see my cursor, by the way. Yes, so this increase in the outcome we formalize as by taking the usual stochastic order on conditional distributions of y. I will give a definition on the next slide, but it just essentially says that if the covariate increases, we expect that all exceedance probabilities of y also increase. Now, IDR can be formulated for covariates in any partially ordered set, but in the case of EasyUQ, and that's also the case that I will focus on from now on, is that the covariates are also just real valued. They are the single valued predictions. And we take just the natural ordering on the real line. So how do we mathematically set up this IDR? So I repeated here the assumption that we work under is we say if a covariate value z is less or equal to z prime, we want that the conditional distribution, this is the conditional law, that's why I denote by this L, is stochastically smaller than the conditional law if the covariate equals z prime. And here you'd see two possible definitions of what this means. So it means that in terms of quantile functions down here, the Q alpha, these are the quantile functions. We want that if z is less or equal to z prime, then all conditional quantiles should increase. Or equivalently, if z is less or equal to z prime, the CDF should be ordered the opposite way. If you would work with survival functions, you would get the same sign of the inequality, but if you work with CDFs, you have to flip it. Okay, now what is this IDR estimator? So what we need for the IDR estimator, we do need some training data. So we have data zi, yi, and we assume for simplicity here of notation that the data is already ordered with respect to our covariate. And then we define the IDR estimator. That's a vector now of CDFs with the same number of entries as the size of the data set. And we define it here point-wise for every possible threshold. So we want to have a vector of CDFs. First, we fix the threshold. And then we take a decreasing vector here because of this flip of sign here that minimizes this squared error criterion, because between the exceedance indicator, that y is less or equal to little y, and here this is the parameter we want to estimate. Now, this minimization problem is a very, very classical problem from isotonic regression that has been studied in the 50s, or started to be studied in the 50s. Here I give you a very classical reference of the book by the Barlow, Bartolome, Brunk, and so forth. So the 4 Bs, where you can find all this. And in particular, what has been derived is you can actually write down a closed form solution to this minimization problem, and it's given down here. It comes in the nice form of such a min-max formula. So this is nothing new. This is really old. What the nice thing is when you look at this formula is that you can, of course, write down this minimization problem, but per se, you have no guarantee that this will be when you then vary y, right? I've wrote down the minimization for fixed y. But afterwards, I want to consider this fi as a function of y. So I have to make sure it is actually a valid cumulative distribution function, that it's so that I get it's increasing and it has the right continuity properties and so forth. Now, because we have this closed form solution, it magically appears that that's automatically satisfied simply because this indicator here, that YL is less or equal to Y, is a valid CDF. If I take averages over valid CDFs, they remain valid CDFs. If I take a finite number of minima over valid CDFs, it remains valid, and a finite number of maxima also doesn't destroy anything. So here, automatically, I get valid CDFs. So this is our IDR estimator. Now, what can we, here is, let me illustrate how this works so that maybe you understand a bit better what I said. Here's a small simulation of how the IDR estimator works. On the bottom, you see 600 draws here from the covariate as standard uniform, and then the outcome is gamma distributed with depending on this covariate Z for the shape and scale. So the black dots in the lowest panel are just the data points that we have generated. Now, suppose you fix a threshold 5. You see that up here, we have a threshold 5. And then the black dots are the exceedance indicators that we had here in this formula. It's the YL less or equal to Y. So those are the black dots. Then this black line is the antitonic regression for these 0, 1 indicators. And if we now want to figure out what is the value of the CDF for covariate value 3, then we have to go here to covariate value 3 at threshold 5. We can read off the probability here, and then if we put down the CDFs, we have our covariate value, we put down the probability, and now you see that if we do lots of these for each threshold, we have to do these antitonic regressions for these binary exceedance indicators, and then we can piece together all the CDFs for all covariate values. Here you see the different examples of covariate values, and this is the full IDR regression estimator. Now, what can we say about properties of this IDR estimator that are favorable? So the first thing about the IDR estimator is that it is calibrated in sample, so with respect to the empirical distribution of the training data. And what this first line here says, it says essentially the IDR estimates are discrete CDFs. And the first line says that IDR is as probabilistically calibrated as a discrete CDF can be. So it says that the probability integral transform of IDR is essentially standard uniform. You just see here, due to the discreteness we have here, we know that when we take the left side limit, it's stochastically smaller than standard uniform, and the right-hand limit is stochastically larger than uniform, but that difference is really minor. You cannot hope for anything better if you have a discrete distribution. The other thing that's nice about IDR is that I wrote it down as this minimization of such criteria here, right, of these exceedances minus the estimate. But it actually minimizes all these integral criteria here. And this means that it is minimizing, it's the optimal solution in stochastically increasing CDFs with respect, for example, to the CRPS, with respect to all weighted forms of the CRPS, be that threshold weighted, that's the first line, or quantile weighted. So no matter if you do this optimization via quantiles, via thresholds, you always get the same solution, and that is this uniquely defined IDR. Now, let me say just a few more words about why we're interested in this calibration property. So calibration ensures that we have a certain compatibility between forecasts and observations, in the sense that the probabilities that we then derive from predictive distributions, they should somehow conform with observed frequencies. And how the most common notion to ensure this is to ask for probabilistic calibration in the sense of a flat pit histogram. So we want, if we take the probability integral transform of the predictive distribution and we plug in the outcome, then that should be standard uniform. And here, again, we need a suitable randomization if our predictive distribution is not continuous, and that was the case that you saw for IDR, why we don't get this exact uniform distribution. In fact, IDR has a few stronger calibration properties. I didn't put them down for simplicity, because for real valued outcomes, there are in fact many notions of calibration, and it's there's a whole zoo of calibration properties that some are stronger than others. And the only exception where everything coincides and where it's quite clear what calibration means is the case of a binary outcome. But otherwise, there's quite a bit of debate, and it's not completely clear what calibration is necessary or useful. But the flat pit histogram calibration, probabilistic calibration, is certainly the most frequently encountered that I have seen. Okay, now how do we compute IDR? Well, for a total order on the covariate, and that's the case when we apply it in the EasyUQ approach, is there's the pooled adjacent violators algorithm, and we have to do that for each threshold that we have observed in the training data, because it's not difficult to show that the IDR CDFs cannot jump at any other point. IDR can be combined with subsample aggregation in the sense that one can compute IDR several times on drawn subsamples from the training data and then average the result. It does is computationally easier, it has less computational cost, and it also gives smoother CDFs, but unfortunately we don't have a rigorous study yet on how should you choose your subsamples and how many, and these kinds of things. So there's some open work here, some open problems. Yeah, there's R package and Python implementation available of IDR. And there's actually also, there's quite a bit of work by some of my co-authors in Bern. So Alexander Hensi, my former PhD student, was involved, and two other people from Bern who actually improved the algorithm for computing IDR quite a bit just over a Pava algorithm on the thresholds. This IDR solution is only defined at covariate values that we have already observed. So what we have to do is we have to interpolate if we want to use it for prediction at a new covariate value. But yeah, that can be done. And if the training archive is large enough, then that's not, yeah, it doesn't make a huge difference how you interpolate. IDR is consistent in a statistical sense. So that has been shown in different works. So for categorical covariate, it's older. It goes back to Albami and Mukherjee. Alexander Mösching and Lutz Dümken from Bern have shown it for real-valued covariate, and then we added the result for vector-valued covariate. And moreover, in the way we want to apply it in EasyUQ is where the covariate is a prediction. Even then, consistency still holds in many cases, so one can even recycle the training data if desired. So what is now the EasyUQ approach that we are proposing? So first, we need to collect training data. The EasyUQ approach relies on training data of single value predictions and outcomes. And then in the basic EasyUQ approach, we apply IDR to the training data with X, so with our predictions, single value predictions as a covariate. And then if we have a new prediction, we then obtain the predictive CDF, our Fx hat, simply by interpolation, as I mentioned before. Now, as I said, this IDR predictive CDF is discrete Sometimes that's a good thing, sometimes it isn't. So if the outcome is known to be discrete, then of course we want this to be discrete, and IDR has the nice property that it automatically learns the support of the distributions we're dealing with. But there are cases where we know that the outcome is genuinely absolutely continuous, so we would also want our predictive distributions to be continuous. And then we apply smooth EasyUQ, where we apply IDR again to the training data with excess the covariate. But for a new prediction, we take a kernel smoothing of the predicted CDF as follows here. So we take this F check X of Y, where we've just smoothed the discrete IDR predictive CDF by kernel smoothing. And this kernel smoothing is done in a specific way such that the stochastic ordering relation is not violated. So that is preserved under this smoothing. And in the paper, we also discuss in quite a bit of detail how to choose this bandwidth H here, or further parameters that the kernel could depend on. That's not completely trivial, because here we're not just taking kernel smoothing density estimate over raw data, but we're actually taking this over this estimated IDR distribution. So that's kind of, it does introduce some particularities that one has to be careful about. Okay, so let me illustrate how this works on two examples with weather data. So the first one is the weather bench data set. It's a benchmark data set that was introduced in 2020 for the comparison of data-driven and numerical weather prediction, model-based weather prediction. We consider from the weather bench data set, we consider temperature forecasts at lead times 3 days and 5 days. And as the single valued forecasts that we compare and that are all available in the weather bench data set is we take the high resolution model output of the ECMWF ensemble, a convolutional neural network forecast that's purely data-based, and a weekly climatology. So that is a climatological forecast stratified over the 52 calendar weeks over the training data. The training data comprises the years 2010 to 2016. And I'm sorry, here's a typo, of course. The evaluation data is from 2017 to 2018. We evaluate the predictions with a CRPS, with a continuous ranked probability score, averaged over all the 32 times 64 grid points in the data set. And here you see the outcome. Let me explain to you what you see here. So first here, the CRPS simplifies to the absolute error when we have point predictions. So we can first just compute, and it simplifies, to the absolute error. So we can compute what are the absolute errors, average absolute errors of the single valued forecast that we have. So we have the climatology, and here you see the values of the CRPS, or the mean absolute error, for 3 days lead time and 5 days lead time of the convolutional neural network forecast and of the high resolution forecast here. Then on the very bottom, as a benchmark comparison, we looked at the distributional forecasts that given by the full ECMWF ensemble with 51 members, where the numerical weather prediction model was run 50 times, well, once for the high resolution forecast, but then 50 more times on a coarser resolution with slightly perturbed initial conditions. And this is computationally very expensive, this ECMWF ensemble forecast, but it should be the best possibility, the best forecast here. So this is the first and the last one. Now, here we have EasyUQ. I'll say something right now, but the CP here is a clear competitor to EasyUQ, would be a conformal predictive system. So this is conformal prediction. And here we compare EasyUQ to conformal prediction because it's also a method that quantifies uncertainty purely outcome-based. So I want to, that's why we've included it here as the main competitor to the EasyUQ proposal. And you see here that in terms of performance, EasyUQ and conformal prediction are not very different. They're actually quite close together for temperature. And you see here that both are slightly worse than the ECMWF ensemble. Now here is the similar table now for if we do this with smooth EasyUQ. Here we have it on, on climatology, on the convolutional neural network, and on the high resolution. We also smooth the ECMWF ensemble. And since now we have absolutely continuous distribution, we cannot only evaluate with respect to the CRPS, we can also evaluate with respect to log score. And the picture is roughly similar. EasyUQ gets a bit more out of the climatology than conformal prediction, but then on the high resolution conformal prediction, at least for 3 days lead time, is slightly better than EasyUQ, and so forth. The second weather data example that we've looked at is an illustration on precipitation data that is more difficult for prediction than temperature because it's neither a discrete distribution nor an absolutely continuous one, because it has a point mass at 0 when there's no precipitation, and then it has a right-skewed continuous distribution given that there is precipitation. So here we have data of 24-hour accumulated precipitation at Frankfurt Airport at lead times from 1 to 5 days, and as the two single-valued forecasts, we compare, again, the high-resolution model output from ECMWF and the weekly climatology as described before. Our training data here ranges from 2007 to 2014, and we evaluate on 2016 to 2017. Okay, so here now you see very similar table as before. First, for the single-valued forecasts, I only put here 1 day, 3 day, 5 days, since there were too many numbers and I couldn't fit it all on the slide. But I think you see the main message. If you compare here the single-valued forecast to the ECMWF ensemble, you first see that this ECMWF ensemble, of course, is a huge improvement over single-valued forecasts. Now, one thing you see here, a few things that you see here that are interesting. If you apply conformal prediction, for example, on the high resolution, you are substantially worse than the ECMWF ensemble. And EasyUQ on the high resolution now, at least for lead time of 1 day, slightly beats the ECMWF ensemble at a much, much, much lower computational cost. Now, why is conformal predictions now all of a sudden worse than EasyUQ? And that comes down to the fact that EasyUQ automatically learns the support of the outcome. It automatically learns that there is a point mass at 0, and then we have something continuous on the positive half line. Conformal prediction in the basic form does put mass on negative values that can never happen. So we also, to be fair, consider it a censored version, and you see an improvement, but it still doesn't get to the nice adaptive and better predictive performance than EasyUQ. Okay, so with this, I would like to come to the end. So we've introduced basic EasyUQ, and smooth EasyUQ has general method to convert single-value predictions into distributional ones. The basic EasyUQ, what we like about it is that it doesn't involve any tuning parameters, and it finds the support of the distributions automatically. So there's really no bandwidth, no nothing you have to choose for basic EasyUQ. For smooth EasyUQ, of course, you have to choose the bandwidth of the smoothing kernel. This EasyUQ, just as conformal prediction, is an output based on uncertainty quantification. So you don't have to have access to the model that actually generated the predictions. You only need the predictions. In the paper, we also have an extensive comparison of uncertainty quantification methods in machine learning and in on the classical machine learning datasets, where EasyUQ is really competitive. It doesn't outperform all uncertainty quantification methods on all datasets, but really it does in the majority of cases. It's the best or the second best method. Yeah, so with this, I would like to thank you for your attention. And here are some of the references that I mentioned throughout my talk. I'm happy to take any questions. I don't see the audience, so it's not that.
Sorry, I think. Yeah, thank you very much, Johanna. And would you have any questions in the audience? Yes, let me come to you.
Hi, thank you so much for your talk. I got a quick question about the last table that you had on the precipitation forecast. So you mentioned that EasyUQ can encode that you don't have negative events, and you also said censored conformal prediction encodes that. So what is now the reasoning in the end why EasyUQ performs better than censored conformal prediction, even because you mentioned before that conformal prediction in the vanilla form still has probability mass on events that cannot happen, but with the censored you don't have that anymore. So what's now what are your insights into why EasyUQ performs better than the censored conformal prediction?
I mean, the centering for the conformal prediction is quite simple, right? It just simply shifts the mass the conformal prediction has put on the negative half line to the point mass at 0. So it's a very simple centering thing that you do. You just shift the mass where you don't want it, you shift it to 0. I think conformal prediction, at least the least squares prediction machine that we have employed here, is really fits to, in first approximation, it fits predictive distributions that are translates of each other. In particular, it fits, these translates all have the same spread. That works super well for temperature, where we are essentially Gaussian and we just move it around. But that doesn't work for precipitation. For precipitation, for higher precipitation, we have higher spread. And EasyUQ just adapts to stochastic ordering, and stochastic ordering, if it's on the positive half line, allows for this increase in spread when the covariate gets higher. And I think that's the key difference where EasyUQ has an advantage.
Thank you. And any other questions? So I think I have one quick question. I mean, I think it's related to Mark's question. So what was the intuition that EasyUQ does not need anything special to learn about the atoms where you have the mass? And also, secondly, how does it perform on when you have extreme values and the heavy tails?
So for the first question, how does it learn the support of the data? You mean like, yes, how does it know that?
Yeah, that looks like the most strongest point of this method. So
yeah. That's simply because it can, when you look at how it's defined here for the, maybe you see it best. Well, I don't know where you see it best. Well, the essential argument is it only puts mass at values that it has already observed. It can only put mass on y-ends you have already observed. So if these y-ends spread relatively well over the whole real line, then you will have something continuous. If you have lots of y's where you had zeros, then you will have a point mass at 0.
Yeah, that makes sense.
That's the whole magic there. Concerning extreme values, the basic EasyUQ doesn't work well for extreme values because it's a non-parametric method. There's no surprise here. I mean, but the smooth EasyUQ, and that's why I said there may be additional parameters that the kernel depends on. The smooth EasyUQ inherits the tail properties from the kernel. And when you fit the kernel smoothing, you can, we discussed that in the paper, you can make sure that the tails that you want for the smoothing kernel do account for tails that you want to predict.
I see. Mm-hmm. Okay, I think we have another question. We can take it a bit, I suppose. Philip has a question.
Thanks for the talk. Very nice. I was wondering, in terms of the assumption of a stochastic ordering, if you have large covariates, like a lot of covariates, is it better to get a subset of stochastic order covariates, or how you check this in some sense?
I don't know if I fully understand the question. Do you mean?
Because like in your example you give, like with the gamma distribution, you have a natural ordering in some sense. But
Yeah.
if the covariates are, how can you check if they are stochastically ordered in some sense in the multivariate way, if it is in a multivariate setup?
Okay, so maybe I answer this in two ways. So for EasyUQ, we really advocate that you have your covariate is your single valued prediction. And since your outcome is real valued, that's real valued, and you have a natural ordering.
Okay.
Yeah, so there I think it's easy. For if you want to apply IDR directly on multivariate covariates, that's of course possible. Then yes, I fully agree with you. The crux is how do you choose the partial order on your covariates? You can, I mean, there are diagnostic plots where you can check that you have chosen that reasonably well so that the stochastic ordering in the conditional distributions is satisfied. We have such plots in, in the paper with on the distributional single index models. But I fully agree with you. If you have IDR with high dimensional covariates, then the main crux is how do you define a good partial order? And yeah, that's not trivial.
Thank you very much, Johanna. Should we thanks Johanna once more and go for the next speaker?